Good morning, and thank you for coming again so early. But I promise you that it's going to be worth it. We have an amazing lineup of speakers in the morning, at least the people who are going to follow me. So with this, let me start. Today, I am delighted to share with you some of the work we have been doing at Databricks over the past year, and I am very excited about. Helping healthcare and life sciences organizations to use big data and AI to improve our lives. Like you heard in the many talks of this summit, the Databricks unified analytics platforms empower data scientists and data engineers to do things faster and easier than ever before, or even do things they were never able to do before. However, as Databricks usage in organization is growing, we are seeing more and more users who are not data scientists, who are not data engineers, but who want to use our platform. So these are domain experts, such as bioinformaticians, mechanical engineers, social scientists, product managers, and many more. And we are very excited about this trend, because these domain experts are the ones who are in the best position to understand what are the business challenges of their organizations. They are in the best position to maximize the value of the data. However, unfortunately, it's a big gap between these domain experts and our platform. Again, this is because these domain experts, they don't have knowledge in data science or data engineers. But we want to fix this. We want to make possible for every domain expert to use our platform to solve their problems. And to do so, we need to bridge this gap. And to bridge this gap, we need to develop domain-specific or industry-specific solutions on top of our platform. In this context, the first industry we have been focusing on is healthcare and life sciences. And today, I am proud to announce the unified analytics platform for Genomics, the first of its kind. In the rest of this talk, I am going to talk about the challenges and the solutions our platform provides to meet these challenges. There are already glimpses of the huge potential of using data and AI to improve people's lives. For instance, Kaiser is experimenting with AI to personalize care intervention. The researchers at the Boston Children's Hospital, they are developing algorithms to predict Ebola outbreaks 1 week or more before it happens. And there are many, many such examples. But as impressive as these examples are, they are just scratching the surface. We are witnessing just the beginning of the revolution in healthcare and life sciences. And at the center of this revolution is the genomics data. By combining genomics data with claim data, with clinical data, with IoT data, with the medical images data, researchers are hoping to achieve faster drug discovery by identifying the mutations which cause a particular disease, to reduce health claims by predicting and treating a disease before it manifests, and to improve patient outcomes by providing personalized treatment for every individual. This revolution is fueled by an explosion in the genomics data. It is predicted that in 2025, the amount of genomic data being produced will be 20 times more than all the video data which will be uploaded to YouTube. And this explosion is driven by dramatic reductions in the cost of DNA sequencing. It took 13 years, and it cost $2.7 billion to sequence the first human genome 15 years ago. Today, by using specialized sequencing machines like Illumina, we can do this in less than 3 days and at a cost of less than $1,000. However, despite this progress, there is a huge challenge to take advantage of this DNA sequencing data. The one big challenge is that the volume of DNA sequencing data is growing much faster than the computing capabilities to process this data. Over the past 15 years, the cost of sequencing decreased by more than 1 billion times, while the Moore's law improved just by less than 100 times. Worse yet, as you know, the Moore's law is coming to an end. So what this means is that the cost of processing the DNA sequence in 1 year is going to grow exponentially year over year. So as such, the current tools and processes do not scale. Furthermore, the entire process of using the data to improve people's lives is brittle and primitive. First, just preparing the data for analysis involved using up to 10 disparate tools, and then you need to take these tools to stitch them together in a pipeline of up to 40 stages. Building and maintaining such complex pipelines is very expensive, time-consuming, and unnecessarily delays the analysis. Second, the tools to perform upstream analysis or tertiary analysis are hard to use and they do not scale. Many of these tools still provide just command line interface, are not flexible, they don't have ML capabilities, and typically run on a single machines. So this means that analyzing petabytes of data in a timely fashion is infeasible. Finally, the disjointed nature of today's tools force clinicians, computation biologists, and bioinformaticians to work separately in their own silos, which further hampers their productivity. Over the past year, we worked closely together with our customers to address these challenges. First, we are providing a library of pre-built, optimally configured pipelines. Thus, instead of spending money and spending time to build and maintain your own pipelines, you can select one of these available pipelines and run it at the click of a button. Second, the unified analytics platform enables users to interactively query the data and use sophisticated machine learning algorithms to get better and faster results. Finally, or third, our unified analytics platform enables users to collaborate in real time and to share the artifacts and the result as soon as they become available. This dramatically improves their productivity. Finally, we have worked closely with the genomic experts to develop genomic-specific optimizations, which reduce the running time and increase the scale by up to 100 times. To wrap up, today we are announcing the first unified analytics platform for genomics, which is orders of magnitude faster and easier to use than existing solutions. These platforms includes a library of best practice pipelines, powerful tertiary analytics tools with AI capabilities, and a collaborative framework. All these capabilities are built on top of a Spark-optimized engine, which improves the performance of many genomic tasks by up to 100 times. By unifying all these capabilities in one platform, we enable healthcare and life science organizations to accelerate the discovery of new treatments, new drugs, and delivery of the patient care. So next, Frank is going to give a demo to illustrate some of the capabilities of our platforms in a clinical setting to improve the patient diagnosis. Frank Nothaft, it's a GTM for Genomics at Databricks. He got his PhD from Berkeley this year, and he is a creator of Adam, a very popular open source system for large-scale genomic processing. Please join me to welcome Frank.
Right. Well, good morning. It's very good to be up here today. Pleasure to talk to you all today. So I'll be talking about a little use case that's a nice, easy to understand one that looks at how we could use genomics in the clinical setting to accelerate care. So when a baby enters the world, we always like to think about about the cute first that we might take a video of or take a picture and send to friends. The first time that a baby speaks. First time a baby smiles. But from a biological perspective, when a baby's born, you have all of these systems that are experiencing their own first. You take breaths for the first time. Your digestive system has to process food for the first time. And typically, this is a very routine transition. The vast majority of newborns undergo no complications at birth, and they're discharged from the hospital in 2 to 5 days after birth. But for some babies, this is a very difficult and challenging transition. And that's why we've spent a lot of time and energy in the medical field working on neonatal intensive care to make sure that we have a good, well understood way to treat common things that newborns present with. Say a premature newborn is born with slightly underdeveloped lungs. We have a very well understood course of treatment for that. Because ultimately, in the NICU, time is critical. And one of the issues, though, that can easily come up is if we have a newborn who comes in who doesn't meet one of these conditions that we understand well, we may not have a rapid way to go from identifying that, we may be able to identify what the symptoms they present with, but we may not be able to identify an underlying condition. If we can't identify that underlying condition, it's very hard for us to actually get to a diagnosis that allows us to guide our treatment. And one of the areas where there's a really big opportunity to leverage genomics is in this space where we're trying to get to that diagnosis. If we can look at the genetic data for a newborn child, we can go ahead and try to tie that back to a gene that we understand where that gene gets involved in other diseases, and that can lead us towards a possible treatment for this child. But as we've mentioned earlier, genomic analysis it's very difficult. We get the data off from the sequencer. We get hundreds of gigabytes of data from this whole genome sequencing run. We're going to go ahead and process that. That might take tens of hours up to a day to go ahead and process through. A day is a long time when we're sitting in a primary care, in a diagnostic setting. When I have that data, I'll get a bag of 4.5 million variants, and I have to go ahead and filter that down to a small set of variants that give me some insight to this disease. So I'm going to use machine learning to identify variants that look like false positives that I should throw out. I'm going to use statistics, and I'll do data integration to pull in population-level databases with gene annotations to find these variants that look like they could plausibly be driving this disease. And then finally, I need to go ahead and generate some report that my clinician can use to guide the course of care. And this final step, right now, the ways that I would do that are very static. If my doctor had this report and they wanted to see a change to the report, they wanted to see more variants that are possibly interesting, they would probably have to go back to a computational person to ask for a whole new report. So here we have this pipeline. It's very slow. There's a lot of manual steps. We have to pull data in and out of a bunch of different tools. So let's instead look at how we can do this with the Databricks Unified Analytics platform for genomics. All right, great. So the specific analysis that we're going to be looking at today is something that we call a de novo variant analysis. And so de novo from Latin, it's we're talking about new variants. And the hypothesis behind this is that if we have a child who is sick, but we have two parents who are healthy, well, clearly any genetic variant that shows up in the parents aren't severely ill, so it's unlikely that genetic variant that a parent would have would be causing the child to be sick. So we want to find any variants that show up in the child that we didn't see in the parent. So what we want to do is we want to load in the genetic data that we have. We're going to run a set of joins to identify variants that look like they're new in the child. We're going to use machine learning to filter down our variants to ones that we have a good reason to believe are supported well by the sequencing data. They're not a false positive. And then we'll start to do data integration. We'll integrate with other data sources, other databases that can tell us more about these variants. And historically, if I was going to run this, I had to cobble together a lot of these different command line tools. We had this long pipeline to generate, to take that data from the raw data from the sequencer, turn it to variant calls. Once I had my variant calls, it takes me several hours possibly to train a machine learning model to do variant filtration. That's yet another tool that I have to run. It's a multi-pass tool. If I want to do that data integration, that data filtration, I then actually have to go ahead and take my variant file and ETL it into another database. Could take about half an hour to an hour just to do that ETL process. That'll finally give me a set of textual, it'll give me a SQL dump of variants that I then have to find a way to go ahead and lift back into my traditional ecosystem of bioinformatic tools, which all rely on genomic-specific file formats. So we have all of these common data wrangling problems that are just kind of rehashed in the vocabulary of genomics. Inside of Databricks, we can instead do this all in a single notebook. We can seamlessly step through it, and we can run all of these steps. We can run all these steps in very interactive latencies. So the first thing that I'm going to do, previously I've run this data through the pipeline. It takes about an hour, hour and a half for us to get through the data for these 3 samples. And what I wind up getting is a table in Spark SQL that has the variant data for my child, my father, and my mother. And if I go ahead and I pull this data in, I'll get a Spark table. It shows up. We wind up having a very large, complex schema for all of this variation data. And typically, this is stored in a flat file format that has this deep nested, hard to parse structure. Instead, I have this in the SQL table. I can start directly querying in an interactive fashion. And in Databricks, we back this with Delta, which allows us to make a bunch of optimizations that are specific to a lot of the common queries that someone in genomics would run. And a really common example of this is a specific query that we want to run to find these de novo variants. So what we're going to do is we're going to run a join that filters out any variants that were in the child that were seen in either the mother or the father. This join makes use of these common genomic primitives for describing where a variant is, and by using Delta coupled with advanced techniques in Spark SQL, we're able to really optimize this. We're able to get about a 100x performance improvement relative to open source Spark. So when we go ahead and we run this whole query where we run the join, we count the total number of possible de novo variants, we're able to run it in just a matter of seconds. So in 5 seconds, we're down to about 120,000 variants left. But ultimately, that's still trouble, right? We ultimately have to hand curate these variants, and I don't know if I could go through and hand curate 120,000 different things. Most medical geneticists wouldn't be able to go through either. So what we're going to do next is we're going to use a machine learning model to go ahead and reify this down to a smaller and smaller set of variants that we're really confident in. And the way that we do this is, we actually have all of these statistical attributes that are attached to our variants that describe the quality of the data. And here, if I go ahead and I run a query and select this field, I can see a bunch of these annotations that tell me how strong my actual support in the sequencing data was for the variants. Immediately, what I'll go ahead and do is I'll train a machine learning model that uses a truth data set. So these are variants from HapMap, which is a population level, a highly validated source. So these are common variants that if we saw them in a person, we would expect, that's a true variant. That's a variant we can be very confident in. We'll use that as a truth set, and we'll train a machine learning model that leverages that. Right now, if I were to run that today, this would probably take 1 to 2 hours to go ahead and train. When I go ahead and I run it on top of Spark, I'm able to train this in under 2 minutes. So that's a vast improvement in runtime, and ultimately that allows me to cut out yet another large step of latency before I can even get to the manual interpretation of these variants. And then when I go ahead and I filter it down, I'm able to apply my model, and I can apply it in a pretty instantaneous fashion. I pass through the whole data set in about 5 seconds. Now I'm down to about 40,000 variants, which is a much more manageable set to look at. And from here, I would typically go ahead and start to do my annotations against these reference databases. These are a lot of common joins and et cetera. But ultimately, I'll have this report that I need to generate. And a very common thing that I'll generate in this report is a visualization that actually shows the read support or the support for the data along with certain annotations put on top of it. So this is what a genome browser looks like. If you've ever had your genome sequencer, this is kind of ultimately what the data looks like. And here we have kind of the genomic variants along with all of the actual raw support from the sequencer that tells us whether that was a true variant or not. And by looking at this plot, we can see, okay, we have this variant that only shows up in the child. What this line here tells me is whether, how many different bases I saw on the read. So I can see it looks like a very confident variant in the child, and I can see I don't really have any support for the variant in the parent. So it does look like a true de novo variant, and from there I can go ahead and work to go ahead and analyze that variant and understand it more. So I hope you all found this very interesting. If you're in the health and life sciences and you'd like to hear more, we'll have a talk about this later this morning at 11 a.m. in one of the developer tracks. But additionally, we'll have a healthcare and life sciences networking event from 4:30 to 7:30 p.m. in room 2022. So hope this was very interesting to you all. Greatly appreciate the chance to speak to you all, and hopefully I'll see some of you all at the networking event tonight.